Hello, good morning. Welcome to Hydronia webinar today. We're going to be talking about the new RiverFlow2D MD module. I hope you can hear me well. If you can, please just let me know with your, it can be in your chat or your questions panel. And we'll get started shortly here. Okay, it looks that you can hear me well. Okay, thank you very much. Thank you for attending this webinar. We are really excited to share with you our recent developments. I wanted to mention before starting that the webinar will be recorded. You will be receiving an invitation to an email with the watch video instructions that you're free to share with your colleagues if you are interested in watching the video a later time. Also, I wanted to say that I hope that everybody, you and your families, are well in these difficult times. And I will be talking about some of the things that we are trying to do to help consultants and companies during these hard times. Our webinar title today is Exploring the Unique Capabilities of the new RiverFlow2D module for Tailings Dam Breaks and Debris Flow Simulations. A long title, but I want to stress here the unique capabilities, because I think what I'm going to be showing to you today is the most realistic model that we have developed up to date to simulate tailings dams and debris flows. My name is Rheynaldo Garcia. I'm the Director of Development and Applications at Hydronia and Hydronia Europe in Spain, in the United States. And I have also will not be presenting today, but we will be presenting the webinar in Portuguese on Friday. Adolfo Correa, which is our representative in Brazil. So we have developed this together, this presentation, in order to show you these new developments. The webinar outline includes some of the challenges that we find typically in tailings dam breaks and debris flow modeling. So I'm going to be talking then about the new capabilities of the RiverFlow2D module. We are going to review briefly the constant property component, so that that will be the first component that we released a few years ago that have been extensively used to model tailings dams and mud flow with these limitations. And then I will discuss the different properties that the new module has, like especially temporally variable density, viscosity, and yield stress, multiple sediment fractions, erosion deposition. And finally, I will be presenting what I think is the most comprehensive test that we have run with this type of model using USGS large-scale experiments data. And finally, I will close with some conclusions. I don't want to start without first acknowledging the amazing team of collaborators that we have at Hydronia. None of the things that we do would be possible without the tremendous help that we receive from this group of people. We have Pilar Garcia Navarro and some others in the University of Zaragoza. Particularly Sergio Martinez is a PhD candidate. He's been extremely helpful. and a key factor in this development, and Javier Fernandez as well, and some of the other people. That's it's an incredible team that I have been lucky to work with, and also I have the team at Hydronia that also is critical help in these developments. Also, I want to acknowledge the funding that we continuously receive from the Inter-American Development Bank. As you may know, the Inter-American Development Bank has adopted the RiverFlow2D model that is distributed as the hydro bid flood in the region, and is done so to help different projects that are being done to support infrastructure investments in the whole Americas. And also, I cannot continue without acknowledging our many users that we have worldwide. They have been also a key factor in supporting our developments, and some of them are acknowledged in this page. Well, so to our topic. Now, debris flows and tailings dams flows are extremely complex phenomenon. I just wanted to show you here a short video of a camera that was recording when this event occurred. But I want to point out here that you have an initially dry bed for the most part. You have an initially diluted flow. Then when the actual flow comes, you can clearly see the changes in difference in density and viscosity that this flow has. It has turbulence. It has different sediment sizes that are flowing downstream. And all of these variables are changing in time. There are numerous videos that you can see, and in this one you can also hear the tremendous sound that this event occurs. But you see, you have many different sizes of sediment and variable properties in general. Also, one of the key things that occur in these events is that the fluid stops at some point. So whatever we do with the model needs to capture this stoppage at some point. Also, the geometry that we find, particularly in urban areas, is very irregular. So we need to be able to capture this irregular geometry with the model as well. So in terms of challenges, we have sharp and fast frontal waves. We have very steep slopes and complex terrain, sudden changes in hydraulic regimes. We have very large velocity variations across the sections. The fluid stoppage, the irregular internal boundaries, particularly in urban areas. And there is also a challenge of when you want to simulate the mixing of runout that is coming from a dam, for instance, with a clear water tributary, and how that mixture occurs, and also that's something that can happen when there is rainfall or when you have a landslide that is coming into a reservoir. As the fluid moves, as you saw in the videos, it can entrain sediment from the bed. So the model should be able also to consider these processes. And last but not least, you have, particularly in the applications of tailing dams, there is an issue on knowing the volume that can mobilize from the tailings. And one of the things that a model should do is at least have a approximation of this volume that can be mobilized. So we I've been developing and distributing the RiverFlow2D model for a number of years, and particularly the MD module, the modern debris flow module, has been used to assess tailing dam breaks. And this is a two-dimensional hydraulic and hydrological flexible mesh model. I stress the flexible mesh here because in nature, it's very rare to find regularity. So if you have a mesh that can be adapted as the model has to any geometry, that's a big advantage, because in many simulations, the obstacles that you have on the way of the flow affect significantly the flow itself. So having a more realistic representation of this surface and the obstacles, it's a key factor. Now, the MD model accounts for hyper-concentrated non-Newtonian fluids. It uses a state-of-the-art finite volume numerical engine that conserves not only the mass, but also the momentum, which is critical in these rapid flows. And it also considers supercritical and subcritical regimes, hydraulic structures, as culverts, weir, bridges, gates. It also considers bridge scour and dam breach. The dam breach component, it's a simplified component that allows you to generate the hydrograph, an internal hydrograph, and runs dynamically with the model. It has seamless integration with two graphical user interfaces, SMS by Aquaveo and QGIS. We have been developing more and more the QGIS plugin because it has a number of advantages in terms of not only software distribution, because it's an open source free software, the QGIS, but also because it has a great flexibility in terms of programming and extension building. The program has a hazard map and animation tool that helps a lot in understanding the hazard that can occur due to these events, and also to visualize the model results. The model runs in standard CPU computers, what we call CPU, which is any computer that you can find off shelf. But also, if you have an NVIDIA GPU card, the model can run significantly faster because it takes advantage of the parallelization that you can do in the GPU card. These cards may have thousands of processors, and the model is capable of parallelizing the computation to achieve performances that were unthinkable just a few years ago. I just mentioned here 700 times speed ups that you can get with the hydrodynamic component. I will talk a little bit about the speed ups that you can get with the new module as well. Now, so far we had 4 modules: the water quality that is related to the pollutant transport module as well. The urban drainage, that is an integration of the 2D and the SWIM model, EPA SWIM model. The sediment transport module that considers bed load and suspended load as well, or combination of these two types of loads. Normally for less concentrated sediment. And finally, the modern debris flows module that is used also for tailing dams. Now, the mesh, as I mentioned, is a critical component of the model because it's what the model uses to make all computations. And it's a great help in analyzing complex geometry areas that you can find in these urban environments. The model uses the full 2-dimensional equations of mass conservation and momentum, and does not restrict any velocity direction, as you may find in some simplifying older models. So the basic computational unit is the triangle. And all the things that we had in the past in terms of the old RiverFlow2D MD module used depth average approximation, single phase continuum model, fluid properties that were the density, viscosity, and yield stress were assumed to be constant. And also we had the assumptions of rigid bed. So there was no material erosion or nor entrainment from the bed. We had, although we had a very comprehensive set of rheological formulations that allowed you to simulate different processes within the flow that included Coulomb viscous relations for granular material, Bingham type of fluids with the latent internal grain sharing relationships and so forth. And that included and 8 different rheological formulations that you as a user could take advantage of. And this is a comprehensive set of rheological formulas that can be adapted to different type of fluids. Now, everything that I have shown so far, it's included in the new version as well. So it's an outline of what we have because we are building on what we had up to now. So also we had the way to, if you didn't know the yield stress or the Bingham viscosity or the density of your fluid, we had a simple tool that allows you to, based on the volume concentration of the fluid that you want to simulate, the model could determine the yield stress and the Bingham viscosity for you. So, and we assemble a number of literature papers where they reported different formulations for the yield stress and also for the viscosity. And that's, again, it's available now. So last year, we used exactly this model to simulate a well-known dam break, tailings dam break that, or failure, I would call, because couldn't be called a break itself. It's a failure of a dam that occurred in Brazil. It's sometimes called the Brumadinho dam, although the Brumadinho is the town that is a little downstream from the dam. So this dam failed in 2019, and it's a catastrophic failure that has some interesting features of what they call the static liquefaction that generated the failure. But also due to the videos and the post catastrophe investigation that occurred, we have some data that can be used to validate the models. And that's what we did with the previous version. We collected data that was publicly available. We also use a high resolution DEM for the conditions previous to the event. So we develop a mesh with the model and makes different runs to analyze the sensitivity of the model with respect to different rheological formulations. And with that, we achieve a pretty impressive approximation of what had occurred in the Brumadinho Dam. And you can see here the left, you see what is observed as the area that was affected by sediment. And here on the right in colors, you have the water that or sediment that flowed, because it was a single phase model. We did a very thorough comparison on different areas to assess how good the model or bad was at different locations. And in most areas, the model was very accurate in predicting the or replicating, I would say, the areas that were affected and depth of the fluid as well. We use these images to estimate the depth of the sediment at different locations. Then we also compare with the model results to get a pretty interesting exercise of comparison. And in this case, the left image shows again the actual event, and on the right a 3D animation with the simulations of the model. So one of the interesting things that we did, I think, here is that we left the model to tell us how much sediment was mobilized. So we didn't impose that as a condition or even based on historic data and so forth. We just let the model evolve from the initial conditions in the dam and then assess what the mobilization volume. And we got pretty good results. The mobilized volume observed was approximately 11.7 million cubic meters, and the RiverFlow2D simulation was 11.66. That's what the model gave us, the mobilization from that initial dam elevation set that we use. Also, the time of arrival of the flow was assessed at different locations. At that particular point that I'm marking with the red dot there, the model predicted 21 seconds, which is a little behind of what was observed, but was pretty close anyway. Now, going more toward the why do we need a variable property model? One of the things that we found here in this application that is also found in many other applications of tailings dams or debris flows is that we have a river here downstream from the dam. This is Brumadinho town. We have Alberto Flores River and the Alberto Flores River gauge. And this is the Paraopeba River, I'm sorry, and the Alberto Flores River gauge that is located here. Now, this is a river with very low sediment in suspension or bed load. So it's a typical alluvial river. And then we have the flow from the dam, which brings a lot of very heavy sediment or concentrations. So when I mentioned that we have a gauge here because when we had the gauge measurements, and as you can see here, this is the stage in the river, and you see here that at some point in time you start to get an increase in elevations of about 5 meters that was forced by the dam, the damming that was created with all the sediment that was coming from the tailings. So at some point, this sediment started to be eroded, and as you can see here, the level in the river starts to go down. Now, what this tells us is that this mix of two fluids created a different fluids that flew downstream. And obviously, with the model that we had last year, we couldn't simulate this accurately. So the simulation needed to stop at the moment that, or couldn't simulate the mixing and what happened with the flow downstream. And that's important because there was a lot of pollution that was a consequence of this mixing downstream. So I have here, this is a cross section of the model results at the Paraopeba River, and you can see here we use this to detect the time that was accurately reported by the model results with respect to what was observed in that gauge station there. So we had started to work on this new model for some time, but all of these events that have occurred, particularly in Brazil, had motivated the acceleration of our development here. So the new model that is already available has a number of new features that it's we couldn't call it a complete new model, but it's almost a complete new model in terms of the number of features that we are releasing. So first is a two-phase model that accounts for several new equations. So we have now not a single equation as we had now before, a single mass conservation and two momentum equations. Now we have the mixture mass conservation as before, but we have the sediment mass conservation, the mixture momentum conservation, and also we account for bed material entrainment. So this is a two-phase model that considers the conservation of sediment and the conservation of the mixture separately, but it integrates that into a model to represent the different processes or exchanges between the phases that occurred. And one other feature that we incorporated is the gravity term that does not assume quasi-horizontal flow. In the typical shallow water equations, one common approximation is that the flow is almost horizontal. Almost, I would say 99% of the models that you find out there have this assumption. And that is totally fine for most of the alluvial flows, but when you're dealing with high slope areas, steep gradients as it normally occurs in dam breaks, this is very important. We have publications I can point it to you that represents that show why is this so important. I will briefly talk about this later. So this is a new term that takes this into account. We also have spatially and temporally variable density, viscosity, and yield stress. So instead of assuming a single density, viscosity, and yield stress for the whole simulation period and the whole space, now these variables can vary, and also they can vary with the entrainment, as we'll see. This allows for modeling multiple inflows with variable fluid properties. So if you have a tributary with clear water that gets into the runout of the tailings or the mud flow, that those two streams can mix and the resulting concentration will vary. So we can also model now the mixing with static fluid. So you can have a landslide getting into a reservoir, and that allows also to account for the interaction of the incoming tailings with water or a stagnant initially water body. You can account for the rainfall and the change of that the rainfall causes on the material density and eventually on the viscosity and yield stress. Also, we included the different bed soil properties from those of the flowing materials. So if you have a tailings that is flowing from upstream, and then the bed material has a different grain size distribution, you can't account for that too. The model works with multiple size fractions. You can have one size fraction, but you can have multiple size fraction with the interactions, and the model tracks the different volume concentrations of each of the tailings fractions, which allows modeling tailings dilution, and also, very importantly, the accumulation of scored material in the frontal wave. All of this is assembled in the set of equations that lead to also the assessments of erosion and deposition due to the flow interaction with the bed material. So it's a lot of things that we added here. We of course needed to change a lot of things in the user interface, and we have now a way to enter the different fractions, the data associated with this fraction, and all the data that is required for the new module as well. I have to say that the new module is totally compatible, backward compatible with the previous one. So the files that you have already, if you have files used in the previous model, you can bring them in here, and then you can add or build upon those. Now, sorry. So how do we validate it, the new RiverFlow2D module? So we typically follow the ASCE guidelines to verify and validate numerical models. This is some guidelines that the American Society of Civil Engineers developed several years ago, that are guidelines to help developers validate models. So there are clear stages that you need to follow, like comparing with simple analytical solutions to check for code errors, try to reproduce experiments and real cases and so forth. So there's a set of steps that you follow. All of the things that we do are in terms of model validation and model formulation, including the theoretical formulations, are passed through the filter of the peer-reviewed journal. So we submit the formulations and the testing that we do, and we eventually publish in those in the papers, and you see here some of the publications that the group has had in the past. In terms of this particular model, there are many other publications related to the other components of the model as well. Now, for this specific module, the new one, we focus on comparing the model with the most realistic control conditions experiment that we think there is. That is, that was developed by the U.S. Geological Survey, USGS. They have a large-scale experimental station in the Northwest United States, and this is actually an ideal setup that can be extremely useful, not only for studying the physical processes that occur in this complex events, but also to generate data that can be used for models for validation. So this is the particular experiment that we use, that I'm showing here, so that if you are interested in having the original reference. So this is the case. So it's a 95 meter, so more than 300 feet long channel, 2 meter wide, and it has upstream a reservoir or a dam that contains 6 cubic meter of saturated debris, and then it has a middle section with sediment bed. So you have concrete for the most part, but it has a section of sediment bed that can be entrained by the flow. And this is the interest here. See how the flow entrains this sediment, and what's the timings, and measure a number of things that are interested, parameters that are interested. So the USGS developed this test. Actually, they did 8 different experiments with variable water content of the fluid, both the sediment bed and also the fluid upstream. It's a variable, it's not a uniform size sediment. You see here, this is a composition in grain size that it has the sediment. And there are many sensors at different locations. You see here at least two locations where they have sensors. You have sensors here as well and upstream. And they measure sediment thickness, normal traction, pore fluid pressure, normalized net force, bed sediment scour depth. So, and there are other things that are measured in time at the different locations. So it's a very comprehensive set of data that is ideal for model validation. Now, at the same time, it poses a challenge because it's difficult in such a complex process. It's difficult for a model to capture all this physics, and that's why we used experiments initially, and even the new development wasn't good enough, and we had to add terms that were missing in our model in order to be able to represent more realistically this type of flows. So this is the plan view and the cut, and you see here the mesh. Just so for reference, one of the meshes that we used. And this is a short video that I want to show you because I will show you later a video of the model results. So this is the initial state. Okay, very interesting, isn't it? Okay, there's several others views. You see, this is upstream. This is the material upstream. This is another view looking from upstream to downstream. This is a slow motion view almost of this area here, but look at the roll waves. This is very interesting. Pay attention to this because I will show you later something about that. Okay, so these are some of the sensor data that was taken. The thickness, the total normal traction was measured with these sensors that you may have seen in the bottom of the channel. The net force, the scour depth, and so forth. That's a lot of information that is obtained from these measurements. Okay, so what parameters did we use in the model? So we had here the parameters. I will not go obviously in all of them, but they were these are the tests, the different water content that was used, the different porosity, bed porosity, the liquid density, the initial concentration of the fluid, and some other parameters that were used in the model to replicate the results. So this is a view of 4 instances of the simulation. So this is the results are 3 seconds. This is the channel in 3D. This is the downstream section. So what you see here in colors is the fluid density. So you see there is a big variation of the fluid density with respect to the flow itself. You see the front is much highly concentrated. Even though the initial concentration is constant, as the fluid moves, it changes concentration because we are accounting for the equations, solving the equations that account for these changes. So this is what we see in the different images in 3D for 3 seconds, 6 seconds, 9 seconds, and 18 seconds. And we see here on the top the volume concentrations of each of the 3 fractions that we use for very fine sediment, sand, and also gravel. So we keep track of this. You see here the changes in volume concentrations as we approach the front. So this is what happened at 6 seconds, 9 seconds, and then 18 seconds. Now look at this. When you see here, the roll waves developing on the slope of the channel. As we saw, we have a roll wave arriving downstream here. We have another roll wave starting to form here. So this is I have never seen before this, and I'm pretty excited about the fact that the model can capture this physics that is a real thing. So we are able now to capture this density variations that affect the area that can be affected in a given event. So it has a very important practical consequences. So this is an animation of what you saw before, only four stages, but this is the animations of what of the whole event. Pretty cool. I think it's pretty interesting. You see here, these are the volume concentrations for each fraction. So it's a very complex interaction of the different sediment fractions that are there, and I think is one very important contribution that I think the model is making in this. Now we did a lot of comparisons. This is not a simple animation. We compare for the 8 experiments that USGS reported. We compare the frontal location. The front location is where the front is. So it means front meaning, let me go back here, the location of the first arrival of the wave here, okay, at each time. So this is the front location measured from the initial release point with respect to time. So you see here that in almost all cases, except on a couple of them, there is a very good resemblance of the model results with respect to the observed values. We did a number of sensitivity analysis, for instance, with different rheological formulations. So this is the front location with respect to time with 2 rheological formulations. Probably turbulent Coulomb is one of the best one that we found here. You see that it's very close. The Coulomb viscous is not as good. But what this tells us is that if we would have had a single rheological formulations that was not the turbulent Coulomb one, maybe the Bingham one, we would have not been able to realistically replicate these experiments. And that also was our experience when we analyzed the Brumadinho Dam Break, which is a very big event with respect to this one, that you have to understand the differences between the rheological formulations, because the most common one was not the most appropriate one to replicate the event, the real event. You see here also the bed thickness is another parameter that we compare with, and the continuous lines represent the model with different formulations, and the dots represents the data, and we can also we got pretty close results here comparison. We also check on the assumption that we have. Do you remember I mentioned before about the term that assumes the local horizontality of the flow that is common in most shallow water models. So If we use that common approximation, we don't get very good results. So by using this new approximation that actually accounts for the slope, the local slope at each cell, it's a much more closer representation, particularly of the front location at given times. These are other results. I won't go into the details here, but for the most part, the relative error of in this case is the frontal velocity. The measure versus computed is very close. There is a difference in one case that we are still looking at. It's a very big difference between the model and the frontal wave. We still are not clear why is this occurring, but we are looking into that. We also compare the debris volume, so that's the amount that was mobilized, and you see here that we are very close in most part with very small relative errors percentage. Also, I mentioned that we use different rheological formulations. And in this case, we also got for the turbulent column or column viscous good results. And you see here the variations in the errors. Now, how fast can the model run? We have the two versions of the model, the one that runs in CPU and multiple CPUs, and the one that runs in GPU that takes advantage of the multiple processors in graphic processing units. So we did a test to check the sensitivity of the model with number of cells. We used 3 meshes, one with 11,515 cells, 50,000 something cells, and 227 803 cells. So in terms of CPU times in minutes, 0.2 minutes. I mean, it's very fast anyway. 5.5 minutes and 70 minutes. This is a much larger simulation if you use one CPU. But when we turn on the GPU component, then we get times in minutes that you can see the tremendous difference. Instead of more than 1 hour, we can solve the same problem in less than 3 minutes here. So with the speed up of close to 27 times. So that means the model runs in this mesh 27 times faster with the GPU card than the one CPU model. Now, bear in mind that the Tesla K40 is far from the fastest now. We have much faster cards now, and we expect that this number, when we finalize the test in the Tesla V100, may end up being close to 100 times faster here. So these times will be crushed. Now, just to finalize, I wanted to conclude with some comments that I think are useful for you to consider. First, that the new RiverFlow2D module is, we believe, an accurate, robust, and fast model that can deal with tailing dam breaks, that can estimate the tailings dam release volume without guessing, meaning that the model will result in that volume for you without having to do some cumbersome analysis of other events and so forth. You can model interaction of streams, lakes, and reservoirs with the high concentration fluids. You can use the model as a general model to simulate hyperconcentrated fluid flows that include erosion and deposition, and at the same time account for changes in material density, viscosity, and yield stress due to the sediment entrainment. And all of this is in a two-phase full two-dimensional modeling environment. You have multiple rheological formulations and integration of the pore pressure term. I didn't delve into this a lot, but the pore pressure term is the one that I suggested that we included that was critical in being able to have realistic results with the model. Without pore pressure term, it's almost impossible to get the results that we obtain. The computation times ended up being with the GPU 52 times faster in using the constant property model, the previous one. And with the new model, it's a less efficient because we need to solve more equations, where still we got 27 times faster simulations, at least based on the USGS tests. And finally, we believe that the model can be a significant support tool to improve emergency action plans for modern debris flows studies, and also for tailing mines. Now, before letting you go, and maybe answer some questions, I wanted to mention that we have an offer for the month of May, where we are offering 30% discount on RiverFlow2D and RiverFlow2D, which is another of our models in our suite of models. So if we want to help people during this period, that we know our companies are struggling, and we want to do the best we can. So by the way, we're offering free licenses to all of our current users that are working from home. If you haven't requested yours, you can do it. If you are a user and you're current in your license, you can request your free license to work from home. And if you want to purchase additional license, or if you are interested in the model for this month, you can take advantage of this this offer. So let me see if I have I don't have a lot of time, but let me try to answer some questions that I have here. Don't you have a closed pipe version of the model that also accounts for slurry flows? No. No, unfortunately, no. Our model is a free surface model, and it does not account for pipe flow. Okay, I have here from Marcos. First of all, congrats for this cutting-edge development. Is there any publication showing the comparison of these new features with the US flume experiment? We are in the process of writing that. That will be submitted very soon. As soon as it's approved, we'll share that, of course, with all of our interested colleagues. Yes, no problem. But we have no. We can share some of the results we have so far, but it's not yet in the form of a publication per se. We have simple drafts. I have here a question: if you have to construct the cross section of the channel, the model, the topography is based on a raster dam or a DM or any other form of digital elevation model, but you don't need essentially to have cross sections in the model. You extract the cross sections for the results. I have a question here. Does RiverFlow2D works with ATI GPUs? Unfortunately, no. We use CUDA, C-U-D-A technology from NVIDIA. That's the language that we use for the development of the GPU version. And that does not support ATI GPUs, only NVIDIA GPUs. Okay, so I think I ran out of time here. And but I wanted to thank you and remind you that this is a recorded webinar. It will be sent to you, the information to watch it later today. I just wanted to thank you for your time and interest, and I'll see you soon in a future webinar. Thank you very much.